Okay, let's continue with Chapter 2, Section 4, Uncertainty in Measurement. A digit that must be estimated is called uncertain. A measurement always has some degree of uncertainty. There's always some aspect of it, the last digit is always going to be estimated. You record the certain digits, and then the first uncertain digit, which is your estimated number. So we have a pen that we are measuring with a ruler, and if we look at it, we have 2.8 centimeters that we are certain of. Now we take the space between 8 and 9 centimeters, this area right here, and we estimate, or we assign imaginary numbers between 8 and 9. And so we are guessing, we are doing our best to predict where that pin is going to meet between the 8 and 9 centimeter mark. So our estimation shows that it's going to be at the 5th millimeter there. So our certain digits are 2.8 because those are the ones that we can actually see, and we are estimating our very last digit. Moving on to Section 5, Significant Figures. There are rules for counting significant figures. Non-zero integers always count as significant figures. Our number here on the screen, 3,456, has 4 significant figures, or sig figs. Zeros. Zeros have some different rules. There are actually 3 of them. Our first one is that leading zeros are zeros that precede all of the non-zero digits. They don't count. So this 0 here is not a significant figure, and this 0 here is not significant. So we only have 2 significant figures, the 4 and the 8. Captive zeros fall between non-zero digits, and they are significant. So this 0 here, between the 6 and the 7, is significant. So we have 1, 2, 3, 4 significant figures in this number. Trailing zeros at the right end of a number are significant if our number contains a decimal point. If it does not contain a decimal point, they are not significant. So our first number on the screen, 9.300, has 4 significant figures, whereas our second number, 150, only has 2 significant figures because it does not contain a decimal. Exact numbers have an unlimited number of significant figures. Exact numbers are things that we count. Okay. Also, just a side note, 1 inch is equal to exactly 2.54 centimeters. So when converting between inches and centimeters, you have unlimited significant figures, but only for that particular conversion. Also, when you are counting things, you have unlimited significant figures. If I count 9 pencils, I have an unlimited number of significant figures because I have exactly 9 pencils. I don't have 9.5 pencils, I have 9 full pencils. Exponential notation. An example of it would be 300 with a decimal written as 3.00 times 10 to the second. Okay, it contains 3 significant figures, and we know that because we have 1, 2, 3. There are 2 advantages to writing this way. The number of significant figures can be easily indicated, and there are fewer zeros that need to be written when dealing with a very large or very small number. Rules for rounding off. These are the same rounding rules that you use in math class. If the digit to be removed is less than 5, then the preceding digit stays the same. So 6.54 rounds to 5.6 if we are looking for only 2 significant figures. If the digit that is to be removed is equal to or greater than 5, then the preceding digit is increased by 1. So 5.68 rounds to 5.7 if we're looking for 2 significant figures. And 3.861 rounds to 3.9 if we are looking for 2 significant figures. When you are doing calculations, you must carry all of your extra digits through to the final result, then round off. This means that you should carry all of the digits that show on your calculator until you get to your answer, then round them off. When using significant figures in mathematical operations, for mathematics or multiplication and division, the number of significant figures in the result is the same as in the measurement with the smallest number of significant figures. So in this calculation, our smallest number has 2 significant figures, so we will do our calculation, and once we reach our answer, we will round to 2 significant figures. For addition or subtraction, the limiting term is the one with the smallest number of decimal places. So here, our smallest number, our one with the fewest decimal places, determines what place we round to. So 7.83 has 2 decimal places, whereas 23.445 has 3. So we will round to 2 places after the decimal. We do our calculation, but we need to round to 2 places after the decimal, so we do our rounding and we get 31.28. Now let's do a concept check. We have graduated cylinders and they have water in them. Okay, we are going to add the 2 together. We're going to pour them into a beaker. Okay, we're going to assume that every last drop of water in these graduated cylinders is poured into the beaker. How would you write the number describing the total volume? Okay, so first we're going to determine how much water we have in our first graduated cylinder. Well, we have 2, 2.2, 2.4, 2.6, 2.8, and we're going to estimate our last digit, which looks to me like it's maybe 2.81. Okay, but that digit is uncertain. Then we're going to move over to graduated cylinder number 2. We have 0.1, 0.2, 0.22, 0.24, 0.26, 0.28, and we're going to estimate our last digit, and I'm going to estimate it to be a 0. Okay, so we're going to add those up, and when we do, we add 2.81 plus 0.280, and you get 3.09. Okay, so we're going to round that to 2 significant figures, and we get 3.1 milliliters. So which one limits the precision of the total volume? Well, our first graduated cylinder, because we are only certain of our first 2 numbers, our 2.8. We estimated our last one. So we know that this one is limiting our precision. Whereas graduated cylinder number 2 over here, it is precise at 2 decimal places. Okay, we had to estimate our 3rd decimal place for our precision. And that's it for this video, guys.